Datadog is a SaaS cloud monitoring and security platform that enables full-stack observability for modern infrastructure and applications at any scale. With seamless integrations with more than 450 technologies, including AWS, PostgreSQL, MySQL, and Docker, you can start collecting and visualizing performance metrics quickly. Set alerts to identify anomalies, collaborate with your team to troubleshoot and fix issues, and release new features to market faster. Try it yourself by starting a free 14-day trial today. Listeners of this podcast will also receive a free Datadog t-shirt. Visit datadoghq.com/HanselMinutes. That's datadoghq.com/HanselMinutes to get started. Hey friends, I'm Scott Hanselman, and it's another episode of Hansel Minutes. Today I'm talking with Anthony Shaw. He's working on Pyjion, a JIT for Python based on the core CLR. How are you?
Yeah, I'm pretty good. It's a bit wet in Sydney at the moment, but otherwise good.
It is a bit wet in Portland, Oregon in the moment right now, but we're inside and we're dry, and we're talking about open source. So 5 seconds ago, I learned that this is pronounced Pyjion. It's Pyjion, but I've known about the project for years, and I've been calling it Pyjion, which is wrong. So I apologize.
Yeah, it wasn't my name, but yeah, it's Pigeon, like the bird.
Yeah. Okay. That's cool. So I'm a little confused though, because if I go up to the Microsoft GitHub and I can see Microsoft/Pyjion with this unique spelling, I see 6 years ago, 7 years ago, and then it kind of stopped. And then it says that development has moved to your personal one. And this one's actually marked as read only. So there seems like there's some history here with this project.
Yeah, the project was started, I think 5 or 6 years ago by two engineers at Microsoft, Brett Cannon, who's also one of the core developers of CPython. So he's one of the main contributors to the actual Python project, and Dino Wieland, who's a compiler specialist. So they started this 5 or 6 years ago with a lot more limitations than we have today. It was targeted against .NET Core 0.9. Which is a while ago, and Python 3.7, which again is a while ago. So they built it as a proof of concept initially, this project. So it's a JIT compiler for CPython. They built it as a proof of concept, only working and supporting Windows, and you had to compile both Python and .NET from source with patches to get it working. So it had a lot of caveats at the time. And they worked on this project for, I think it's about 9 months. And I actually submitted some pull requests because it was an open source project. I submitted a couple of changes. One was to upgrade it to .NET Core 1.0 when that came out. And then to also upgrade a few other things.
I just for a sense of history here, Dino Wieland, I was talking to him in March of 2008, and I've got blogs going back to July of 2007 when Dino showed the Django web framework running on IronPython. So, not just, yourself, the whole community is interested in doing, unusual things with Python and getting it to run in unusual ways. So let me ask you this. The regular folks out there in the world who pick up Python, they download Python 3, they make their first .py file, and they run it. They are largely, as just new people, unaware of all the different ways to take this language and compile it in different ways, run it in different ways, interpret it in different ways. What is it that's so fascinating about Python that people want to try these different ways to run it in different execution environments?
Yeah, so if people download Python from python.org, or they use the Python that's on the Windows Store or the one that comes bundled in macOS, or they install it in Linux from apt or yum, it's going to be CPython. Okay. So CPython is the main Python interpreter. It's the one that 90+% of people use. It's written in C, which is why it's called CPython, which is a bit confusing, but yeah, the actual main interpreter is written in C. It's an interpreted language, and it has a lot of optimization specific to each operating system. One of the big challenges with C Python and Python in general is that the performance of algorithmic code, especially mathematical code, can be challenging because for a number of different reasons. I gave a talk on this a few years ago at PyCon called "Why is Python Slow?" And I talked about some benchmarks comparing Node.js, Python, C, C++, C#, and compared the n-body problem, which is a sort of famous math problem that calculates the orbits of the jovial planets. So Saturn, Jupiter, I can't remember the other ones. It's basically just a big calculation, and it runs that like 10 million times or something.
Right. It's a celestial mechanics problem, right? If you look at how the two bodies or n number of bodies and how they interact, and then if you like to apply that to the solar system, it gets really complicated.
Yeah, it gets complicated. It turns out Python is quite bad at this algorithm, upwards of 100 times slower than many other languages. And in that talk, I basically explained why that's the case.
Okay, so most people out there are are running a interpreter that interprets Python code, and and that interpreter is written in C, hence C Python. There's a long tail of lots of Python compilers. There's Jython, JPython. There's Iron Python historically that we talked about that Dino and them did many, many years ago on the dynamic language runtime, or the DLR. There's commercial ones you can buy, like Active Python from Active State. There's even like Pyjamas or Pyjs, right? But what is it that these things are doing? They're all just coming up with different ways to make it faster using existing runtimes. Is that what these different systems are trying to attempt to do?
It depends. So PyPy, PyPy, is probably the second most popular Python interpreter. It's called PyPy because it's a Python interpreter written in Python. It has a built-in JIT, and it's very efficient at math and algorithmic code. However, it's got a few limitations, such as a lot of Python extensions that you download from PyPI, like the Python package repository. A lot of extensions are written in C, and they're compiled. And because the PyPI interpreter is written in Python, then it can't load C extensions. So it's kind of like a compatibility trade-off. And then the long tail that you talked about, like Jython and IronPython and stuff like that, most of those were built in order to have interoperability into another ecosystem, such as Jython into Java, IronPython into .NET. So they're kind of targeted at not necessarily solving the performance problem, but actually in Python, can I load stuff from the CLR? Can I load in like system namespaces and things like that?
So when we learn about the basics, like the difference between an interpreter and a compiler in school, simply spoken, they basically say that you're evaluating each line as you go, and then they always give an example of, I'm doing this in a for loop, and the interpreter looks at this repeated line that it's no doubt seen a million times before, and it looks at it like a newborn baby, and it says, this is the first time I've ever seen this line of code. Then there's interpreters that can do caching of instructions and things like that, like on a line-by-line basis. Is there kind of like we always teach that in school, like interpreter, compiler, or interpreter, jitter, compiler. But it's more of a gradient, isn't there, as you think about ways to optimize code?
Yeah, it's a gross oversimplification, I think. It's fun if anyone out there is interested in compilers, go and look up the original version of PHP, like 1.0, I think it was. The source code is out there somewhere, and you can see like that's a fairly crude implementation of a interpreter. Definitely doesn't do it line by line because you can imagine you've got if statements and you've got for loops and you've got things where the next line doesn't actually relate to the one before it. So even Python compiles things, like it just doesn't compile it to machine code in the same way that a C++ compiler would. .NET is similar. Like .NET doesn't compile to machine code. It compiles down to bytecode, and then it runs that bytecode, same as Java. So most languages will all have a compiler. Just the question is like, what does it compile down to? And in Python's case, it compiles down to bytecode, which is cached on the machine. And then at runtime, it runs that bytecode. And these bytecodes there's about 150 different operations. And there'll be things like add two variables together, or subtract two variables together, or call this function, or call a method. And each bytecode takes a single argument. And it basically pushes and pops values from a value stack in the interpreter.
Mm-hmm. So I've sometimes called that, when teaching classes, a processor non-specific assembly language. Mm-hmm. Right? It's just kind of, and I've even used the analogy of like using a food processor to chop up like apples. You want to get apple juice, but we're going to take it to apple sauce, and then we're going to stop, and then we'll ship the apple sauce around, and then we'll let the last moment. So if I give you IL and I have an x86 machine, and you have an x64 machine, we will consume the same intermediate language, that same applesauce, but you're going to go in just in time, you're going to compile it for your processor and your amount of memory and your instruction set and all the little details about your computer that may be different from mine. That sounds like a good thing. It sounds like an almost perfect thing, but then there's issues around startup, right?
Yep.
Yeah.
Yeah, so that's one of the big challenges with JITs. Is that typically they have a big startup time, and Python has a lot of usage in areas where you want it to have a short startup time, such as standalone scripts and being used inside Docker processes and in places where you want it to start really quickly.
Mm-hmm. Okay, so then you come upon Pidgeon that was worked on by some lovely and amazing compiler geniuses, but then was it abandoned, or was it forgotten, or was it left on the side of the road? Why did it stop, and why did you fork it?
It was written as a proof of concept, and there were a few proposals in there to make changes to the C Python spec in the form of a PEP, which is a Python enhancement proposal. So when you make changes to Python, somebody has to write a proposal and a specification, and then it gets reviewed, a bit like an RFC, request for comment in internet land. And Brett basically put together a PEP, which was accepted and then integrated into Python 3.7. And then I think they kind of took the project as far as they wanted it to go at the time, and then it was put on the shelf. No more engineering time was put into it. I picked it up a few years later, actually after finishing writing a book. So I've written a book on C Python, like how it works, and called C Python Internals. And kind of once I'd written this book, I was just really curious about like how could you make Python faster, and that's the area of research. And I just wanted to write a compiler. I thought it'd be fun. So often the best way to write something that you don't know how to do is to take a project that somebody else has written and then rewrite it. So at least you can do it in baby steps. Like if you just start from scratch and say, I'm going to write a compiler, and then get one of the famous books, it's going to be a lot harder than picking a project somebody else has done and rewriting it.
I've talked before on the show about the joy of nerd sniping. Are you familiar with that term, right?
Yeah.
It seems like you got nerd sniped. You're just like, I think in my copious spare time, I'm going to write a compiler. And then you just can't let go of it, right? By the way, this show is somewhere in the 800s or the 830th show in the Hansel Minutes catalog. I was looking back on the catalog and noticed that I talked about IronPython in episode 45.
Wow.
And here we are in the 800s. And I've also spoke with Dino. You could check him out at Hansel Minutes episode 384. So we've got a lot of Python content here on the show, and a lot of history. So you pick this up. You say that this project has got good bones, as we say. Like it's a fixer-upper kind of a house, right?
Yeah. So
you buy this house, you fork it, and now rather than living at Microsoft /Pidgeon, it now lives at Tony Baloney /Pidgeon. And we trust Tony Baloney because you have more stars. This is very well thought of. And of course, you can check it out at trypidgeon.com. I'm going to put links of all of this in the show notes. And how long did it take you to get it to the point where you felt like you had something good, and then you were going to start really working on this in earnest?
About 6 months.
Yeah.
Yeah, my C++ was rusty, so that was one thing. And yeah, compiler projects are quite challenging. Also, I think I wasn't prepared for debugging JIT compilers, like how hard that is. So I had to do some homework first. So, when you're debugging pretty much any other language, you can put a breakpoint in your code, and you can execute the code, and the debugger will pause at a breakpoint, and then you can see your variables, and you can see a call stack and things like that. When you're working with JIT, there are no breakpoints because it's compiling down to machine code. So a lot of the time, if it crashed, I'd be looking at assembly, pages and pages of assembly, and then trying to understand what was happening in assembly, which doesn't fit in my brain. Like I can't visualize CPU registers and allocations and stuff like that. So quickly realized that what I needed to do was to write tools to visualize what it was doing, to help before I get to the point where I'm staring at assembly. So kind of what I focused on then was basically writing different output tools, like graphical outputs at the compiler stages, so that when it would spit out graphs and stuff for me, that I could then look at what was going wrong and what could be optimized and things like that. So yeah, that's what's on the website. If you go to live.trypyjion.com, there's like a live version of the compiler. On the left-hand side, you've got the Python code, the demo code, and then you can click the compile button, and you'll get a couple of printouts. One is the CIL, the .NET CIL. The right-hand side is the assembly code, and then if you scroll down, you get the instruction graph. And then further down, you get something called a control flow graph, which is something that's typically used in compiler and interpreter design.
And then that term that you just used, CIL, C-I-L, the Common Intermediate Language. So we'll put this again, a link in the show notes, but what we're looking at is basically CodePen for Pidgeon. Python on the left, the center square shows you all the intermediate language, and then you get the final assembly language on the right. And, for those of you who are not assembly language people, like it's the closest thing to watching the Matrix and looking at the characters falling from the sky. And then people who can look at that and see a picture in their mind are amazing people who can read assembly. But it is definitely a challenge to draw that straight line. I'm sure you can do it better now that you've been working on this for so long.
I had to get a book on x86 64. The excellent book actually by Joe Van Huey. I recommend that one. And actually sit down and write applications from scratch in assembly so that I had a better knowledge of it. It's something that I must have skipped at school. I must have been asleep during those lectures, but yeah.
I missed that one as well. At the end of the day, your customer has to be at the center of everything you do. This starts with the right customer data strategy, as well as the right foundation to solve the challenges that typically inhibit the success of your company, such as data quality, data governance, and connectivity. mParticle is your real-time customer data infrastructure that helps you accelerate your data strategy by cleansing, visualizing, and integrating your customer data from anywhere to anywhere. Ultimately, better data leads to better decisions, better customer experiences, and better outcomes. See why the best brands choose mParticle. Go to mparticle.com. That's mparticle.com. All right, so let me try to break this down. I want to understand this pipeline because this is not the same. Like IronPython took Python textual language and it interpreted it into a thing called the dynamic language runtime, and then at runtime tried to run this code in place. Yep. This is not technically it's not running Python on the CLR. You've picked your favorite part of the .NET framework. The .NET framework consists of compilers, a jitter, a garbage collector, a runtime, a base class library. You picked the jitter, that one piece that you liked the most, correct? And you're not running Python on .NET. You're just running it through a pipeline, of which a portion of .NET that you've taken?
Yeah, so one of the major changes with .NET 4 and .NET 5, it's like it's a single number difference, but in terms of the actual project and the code, it's like completely different. So .NET 5 was previously called .NET Core. It's cross-platform. It comes with a JIT that supports both x86, 64 like Intel CPUs, and it also supports ARM. So if you're running on a Mac M1 or you're running on a Surface X, I think it is, with an ARM CPU.
Surface Pro X or a Raspberry Pi.
Or a Raspberry Pi. So .NET 5 and .NET 6 are basically this new .NET architecture. And one of the components is a thing called I don't even know how to pronounce it.
RyuJIT.
RyuJIT.
It's RYU.
RyuJIT. So RyuJIT is a JIT compiler that compiles .NET's intermediary language, the CIL, into assembly code. Basically machine code which can be executed on Mac, Linux, Windows, and both Intel and ARM CPUs. It supports 32-bit CPUs as well, which I find astonishing in 2022. But somebody must be running them still somewhere. So as a JIT compiler, there are a team of engineers at Microsoft that are absolute experts in JIT compilers, and they've been working on building this thing for over a decade now, I think. It's highly optimized. It's highly efficient. It has excellent debugging support and output. So what Pidgeon does essentially is it takes Python's bytecode. So that would normally be given to the CPython interpreter. And just when you execute the function or the class or the module or whatever, it grabs that bytecode and then it transpiles it to CIL. So basically says, okay, well, this Python bytecode add two numbers is equivalent to these CIL instructions. And it basically creates the CIL, so it sort of transpiles it to CIL, and then give that CIL instructions to RyuJIT, which then compiles it into assembly code. And then you put that assembly code in RAM, and then you tell the CPU, go and run all the instructions at this memory address, and it runs the code. So it essentially compiles Python code down into machine code, and then runs that just in time, hence the JIT acronym.
So then that means that RyuJIT as an input takes the CIL, the CIL, the common intermediate language, and doesn't know when it consumes IL from whence it came. It doesn't know if it's C# or Visual Basic or F#, or in this case, Python. It just happily accepts a standard intermediate language, which is a standard. It's an ECMA standard. And there's nothing in it that gives it away. There's no way for RyuJIT to know that Python is incoming, right?
Yeah, that's correct. I think Pidgeon is the only project that uses RyuJIT as a standalone thing. So it's been a fun journey working with the engineering team all through GitHub. So .NET 5, .NET 6 is all on GitHub. It's all open source. So any feedback and stuff that's been given, any tests and things have all been on the GitHub repository, which has been really cool. So all the work I've done with the compiler team has been as a contributor, as Tony Baloney, not as a Microsoft employee. I think they didn't even know that I worked at Microsoft. It was just like, oh yeah, I've got a whole bunch of questions about how to do this, that, and the other. Yeah. And we just kind of do the whole thing in the open. So
that's awesome. Like a lot of folks who may have been around for a while may be familiar with a popular compiler book that's called the Dragon Book. And the Dragon Book taught us compilers in school. And Ryu in Japanese means dragon. So then RyuJIT is a dragon JIT, just like the dragon compiler. And then Ryu was also a hero in Street Fighter, the video game. And he would yell, Hadouken! And then shoot his fireball from his hand. So I believe that is how the RyuJIT name was chosen. So there's always some layers there deep into the system.
I just learned something new. Thank you.
See, that's the value that we provide here at the Hanselman. It says the compiler genius comes on. I can tell you at least how. Look at that, and there's the Dragon compiler.
There's the book. Yep, it's on my shelf behind me.
He pulls it off his shelf, but the credibility bookshelf behind you with the compilers and stuff. Okay, so you're the only project that's using it as a standalone thing. There's no CLR involved. There's no garbage collector involved. This is because you liked a piece of pipe in the pipeline and decided to put things in one side of the pipe and it pops out the other side of the pipe. Did you ever find that it didn't do what you wanted? And you're like, oh, this is not possible. I should never have tried this.
Yeah, so in order to use the Dragon JIT now, that's easy to say. In order to use the Dragon JIT, you have to implement an interface in C++ that comes from the API. So you have to implement a set of methods. I say set, so there's about 160 methods that you have to implement. And some of those are, they relate to managed types. So I could briefly explain managed types, although you probably know a lot more about them than I do. But in .NET, you've got low-level types, things that the CPU would natively understand, such as 32-bit numbers, 64-bit numbers, floating point numbers.
Intrinsics. They're intrinsically just there available to you.
Yeah. And then you can also do things like you can define classes and you can have inheritance and things like that. So that's the difference between int with a string with a big S and string with a little s, isn't it? In .NET.
Well, so yeah.
That one always confused me.
In .NET, when you say string with a lowercase, all lowercase, it is ultimately system.string, but then it maps to, something. So it is the same thing. You can say system.string, you can say system.int32, or you can just say lowercase int. It's like an alias for an intrinsic thing.
Yeah. So .NET's type system, the fact that you can use it from C# and F# and Visual Basic .NET and C++ as well. The fact that you can use the type system from multiple languages means that it's a managed type, and there's a whole bunch of infrastructure behind that, all these APIs behind that. Now, I didn't want to implement a Python way of doing managed types, and I didn't want to reflect Python classes into managed types because the spec for managed types is in ECMA 335, which is the CIL spec. So when we say CIL, we're typically talking about that spec. It's a massive description of like how managed type should work, how int methods work, like the type system basically of .NET is described in that document. I didn't want to implement that for Python. It's kind of like trying to smash a square peg into a round hole in a number of areas, like how Python does classes and how it does like things like multiple inheritance, and it doesn't have interfaces.
Yeah. Well, that's one of the challenges with the DLR was trying to go and map between these two worlds. And using my awful apple juice analogy, this would be like taking oranges and trying to get applesauce. And at some point your abstraction's going to leak and you're just going to have a mess, and all I wanted was juice. So yeah. So you sound like you punted on that entire thing and just decide to be a little more low level than that, as opposed to biting off the entire managed type specification.
Yeah, exactly. And in Python, everything is an object. Well, everything is a Py object, which is a pointer to a simple data struct that has a type. And then everything kind of like flows on from that. Now that's great that everything is an object, but it also means that things like intrinsics are also objects. So numbers, which like I always think of CPUs as just basically being calculators, just very fast ones. They can only do a couple of things: move numbers from one place to another, add numbers together, subtract numbers, and divide numbers, and that's pretty much it. Like CPUs don't do a great deal more than that, but they're very efficient at those things. And because in Python integers are objects, every time you do a calculation, if you've got values in between the answer, like let's say you had a times b times c, well, in order to get to the answer, you have to multiply a times b, and then you have to multiply that result by c. So what Python does is it creates the result of A times B and allocates that as an object. And then using its reference count in the next instruction where it multiplies that by C, it then decrements the reference count and then deallocates the object. In turn, that makes Python very slow at those types of calculations. So the n-body problem that we mentioned earlier, like that's why it's so slow at doing that, because that's all floating point numbers. Right. And Python is just constantly allocating and deallocating memory and creating all these temporary objects.
I see. So it's doing a bunch of calculations, and it's a bunch of administrative overhead running around on the heap when they could be doing a bunch of very quick stack math work.
Exactly. So what Pidgeon does, and what you'll see in the live.trypidgeon.com example, is just exactly what I've explained, which is a function in Python that has A, B, and C. A is the number 2, B is 3.0, so it's a floating point number. And then the next instruction is to add the result of A times B. And what Pidgeon essentially does is it looks at the Python code and it says, A is an integer, B is a floating point number. Therefore, when I transpile it into CIL, I'm going to define some locals, because CIL also has basically numbered locals. So when you're writing a C#, you normally give your variables names. The compiler doesn't compile them into names, it compiles them into numbers. So they're like variable 1, variable 2, variable 3. And so what I do is basically compile those variables down into numbers and then give each of them a intrinsic type, which in this case would be a 64-bit integer for the number 2, actually 32-bit, and then a floating point number for 3.0 and a floating point for 4.0. And then the CIL instructions for the actual math component, which is a multiply. There's a multiply instruction in CIL. And when the .NET compiler gets those CIL instructions, it does its own optimization to say, I see you've created these 3 variables and you've said, let's add them and then multiply them. But actually, there's no way that they can change because they're constant. And therefore, I'm going to do something called constant folding, where I actually work out the result ahead of time and compile that into more efficient code. So RioJIT, the Dragon JIT, is basically done is I've borrowed a decade worth of engineering from that compiler team, all this optimization work, which basically takes intrinsic operations and then compiles that down into very, very efficient assembly code. So the assembly code that gets spat out at the other end, I think basically just loads the number 12, calls a Python API call, and then returns it back. So yeah, it's very efficient.
So as we get towards the end here, one of the last questions that I had for you was in Python, there are native modules. And native modules, there's 2 different formats for Python. There's different packages versus shared libraries and things like that. I know I bump into these things with Node a lot, where everything's great until someone has to call C code. And in the .NET world, we do a thing called p-invoke or platform invoke, where we can call an extern C or a C function that is shaped a certain way. It's like a lollipop. And you say, I can call that. What happens when you are bringing in python.py files and then suddenly you hit native code? How can you just nicely interleave that native code into the native code that you just generated?
Yeah, this is a tricky thing. So in Python, if you want to run C or C++ modules, that is actually quite easy to do. Similar to p-invoke, Python's got its own API for importing modules, whether those are things like shared libraries or DLLs, and then calling functions on those. It also has ways of converting C structs, so like low-level data structures, into dictionaries in Python or simple types. So Python's kind of got all that stuff built in. It also has in the interpreter a way of calling functions that are in other shared libraries. So all of that stuff you get in Pidgeon. Any code, but big focus has been on compatibility. So if something runs in CPython today, and it should run in Pidgeon as well. So I've put a lot of effort into compatibility. When it's compiling, it can't make any. If it has any issues or anything, it just bails out early and it says, "I'll just let CPython handle this one." The user doesn't notice any difference. with the native code, that's kind of how that works. I have looked at whether you could call managed assemblies from Python using this, but that problem has already been solved with the Python.NET project. And I kind of got the sense that I'd be reinventing the wheel, and it wouldn't be a good use of my time.
Well, I think that writing this, though, the whole Pidgeon project and bringing it back, keeping the name and moving it forward and doing a totally different way, and the cleverness of pulling in the JIT is really just a wonderful use of your time. And I appreciate you hanging out with me today.
No, it's been a good chat. Thanks, Scott.
Yeah. You can check out the great work that's happening at trypyjion.com. Again, we'll put that link in the show notes. It's trypyjion.com, and see a live demo in your browser without downloading anything at live.trypyjion.com. This has been another episode of Hansel Minutes, and we'll see you again next week.